Good morning, everybody, and thank you very much for your time. My name is Kanan Soundarapandyan, and I run the high voltage isolation products business for Texas Instruments. The person's name you see on the slide is actually the person who does marketing manager for my business. Today the topic is going to be talking about capacitive isolation and fundamentally how it strengthens any industrial system that it's built into. We are from a Texas Instruments perspective, this is a key and critical technology for us. We've been placing a lot of importance on this and investing heavily in these technologies, and I'm very happy to actually bring those to you today. Okay, a couple of basic starting information over here in terms of why and where isolation is relevant in today's connected world, right? There are a lot of system trends that are actually driving need for isolation across the board, especially in the industrial marketplace as well as automotive also. Three things that I'd like to talk about over here, and by no means are these the most, is this a comprehensive list. There's many other advantages over here, but I'll talk about these three. Robustness in high voltage systems. I mean, more and more today when you look at different systems, whether it's a question of transferring energy from the place where it is actually generated into the place where it is used, or on the other side of things, transferring information from one place to the other across long distances, what is needed the most is robustness in high voltage systems, which basically means the device needs to be able to take all the harsh conditions in the world, whether it's an EMC kind of an event, an ESD, some kind of short circuit, whatever have you, it needs to be able to handle such fault events in the world and still be able to keep on taking. Reliable operation in harsh environments. It's the same, it is part of the same theme that I'll be talking about for the rest of this particular presentation as well. Reliability is key. For example, if you are in the middle of a signal path and a small microcontroller somewhere tells a very large 600 horsepower motor to start turning, for example, at that particular point in time, no single bit of information can be missed. So reliability is also key, especially in very harsh industrial environments. Smaller package and system size. One of the key benefits that digital isolators today and these key isolation technologies actually deliver to system level, from a system level advantage standpoint, is the size. Today, for example, we have packages that are less than 4 millimeters in size in each dimension, but can actually have 6 channels within them. So from a channel density, as well as capability to run at higher temperatures, as well as just creating a much smaller system goes, these devices, you cannot beat them. So again, to touch briefly again upon where isolation is needed. First of all, in front of me, you will see on this slide, there are many areas that I've actually called out separately. But the key thing to notice over here is that this is just a very small list of the places in which isolation is used. Today, we are seeing the need for isolation anywhere, wherever you have more than one energy source, or whether you have information going over long distances, the need is absolutely there. These are some of the top areas in which TI is focusing on from an isolation technology standpoint, and these are the areas where we see most of the needs coming from today. So I'll go through the first three and then I'll wait, and then we'll go through the other three after that. I'm going to talk about maybe a couple of places over here. Perhaps you can, yeah. So I'll just talk briefly about a few of these different market areas that we've got on the slide over here. First one, let's talk about factory automation. I mean, we've heard now that the levels of automation in a factory are going up exponentially. That is, older systems that used to work through mechanical linkages, hydraulic linkages, and even very rudimentary electrical systems are being upgraded now with the latest in automation. You have PLCs, you've got sensors, you've got drivers, actuators, and the number of such links in a factory floor is just exploding. But however, if you think about it, on the one side, you may have a microcontroller that is running at 1.8 volts or 2.5 or 3.3 or whatever it is. And on the other side of that link, you may actually be sitting 100 meters away from the control room with maybe a 1,000 horsepower motor that you need to control. So if you think for one moment that when you when the command comes from the PLC for an actuator or something high energy to turn on, now all of a sudden, the two grounds in between these two different control elements could be separated by about 50 meters to 100 meters. And at that point, the ground differential just by itself needs to be taken care of. If you think about that for one moment, you'll now know that you need an isolator or some kind of protective element in the middle of the controller and whatever actuator is being controlled, just to make absolutely sure that because of these ground potential differences, nothing gets damaged. So now if you start thinking about the fact that you've got an exponential growth rate in the number of information links, last mile links in the factory, you need an isolator on both sides of that just to keep everybody happy and for not one element to kill the other. This is how important isolation is. Another one I'll also choose to talk about right now is motor drives. Again, it's a very telling example of just where the world is going and why isolation is necessary. Same thing here. If you think about the fact that most motor drives, all the way up to a 690 volt industrial motor, all the way down to something that runs at 48 volts, your control systems are probably at much lower voltages. Let's say your microcontroller, for example, is at 3.3 volts. And yet, you need to control a very large energy device, like a motor that's sitting on, say, a 1000 volt bus. At that point, you need an isolator to be able to do that level shift. So for example, something that's able to take a control signal at 3 volts and translate it to be able to operate and run a very large motor at 690 volts on the bus, for example. So this needs an isolator that's able to do that with zero errors reliably over lifetime in very harsh environments. The last one I'll talk about also is automotive. You can actually see OBC is onboard charger and BMS is battery management systems. HEV EV, I don't think I have to tell anybody here in this room, is basically seeing growth rates that are phenomenal. Most cars and most car companies today have strategies that take them into HEV EV almost immediately in this new future. The same things that we talked about, both for factory automation, where you're talking about information over large distances, as well as motor control, where you need to do a level shift from low voltages to high voltages, exist in automotive as well. And we today are seeing a lot of traction for digital isolation technologies in HEV EV as well. So just going a little bit more into details about what we briefly discussed before. I mean, why is isolation actually needed? Very simply, this diagram over here shows you what the point is. If we think today about the real world, that is any factory environment or even a building environment or essentially any world, any place in the world which has any of these particular items that need to be measured. So for example, temperature, speed, position, flow, pressure, sound, light, and humidity are all things that we measure not only in factories, but in buildings, in cars, in pretty much any system today that needs any amount of automation. These are the real world signals that we need to measure with varying degrees of accuracy to be able to make decisions on that basis. The key point I will make over here, however, are that these are all elements that are measured at different places. For example, a temperature measurement in a factory may need to be done at everywhere on your assembly line, for example. All that information needs to be collected and sent to a PLC or a computer system somewhere that will make decisions on that basis. To be able to do that safely, as well as not damage one part of the system from the other because they're separated, you need an isolated barrier on both sides of this particular communications link. So this illustrates very clearly what I'm talking about. For example, you could have something like a CAN or an RS-485 bus going from, say, a sensor or an actuator all the way back to a microcontroller or PLC somewhere, and you need this isolation barrier in the middle to do that in a safe manner. So that brings me to the actual technology that TI has been using for the past, I'd like to say since almost the early 2000s, since 2001. So we've been doing capacitive isolation technology for a very long time, and we have a very good idea of essentially what the technology is capable of and what advantages it actually has. So for example, if you look at this table over here, there are many technologies today that can do basically isolation, the isolation function. Just for comparative reasons, if you look at the dielectric strength of air, what that means is how much voltage do you have to apply to air for it to actually break down? You'll see that the value is about 1 volt per micrometer is sufficient to actually break air down. So that works out about 1 kilovolt per millimeter. That is the intrinsic breakdown capability of air itself. Now, if you look at other materials, epoxies, silica-filled mold compounds, polyamide, these are some of the competitive technologies that are available today. TI has selected to use SiO2, which is silicon dioxide, which is essentially glass. And the reason that we've chosen to do that is simply because the robustness and reliability of a glass-based solution, as well as the performance level from a high voltage perspective, is unparalleled. Just to give you one example, the dielectric strength itself of glass compares very favorably to every other technology out there. You can see that we've got 500 volts RMS per micron. It's in fact, it could even be larger than that compared to all the other technologies over here. So this actually allows us to do significantly better controlled and high precision, high voltage components so that we get the performance that you can see in our data sheets today. A major reason why we're able to get that kind of performance and why we're able to make the claim that we have the highest, longest lived isolator materials as well as the highest reliability is because in one part at least of the materials that were selected. So also coupled with why we have such good performance from a parametric standpoint is the fact that we couple this excellent materials and the very capable material technology with also the way we architect the entire system itself. If you look at it, we use 2 capacitors in series, as you can see from this diagram here. This is a cross-section of a device of most devices that are released by TI today. You've got 2 dies, 2 silicon dies, and each one of them has a high voltage capacitor. Being able to do a double insulated capacitor system like this provides significant advantages in terms of the fail-safe capability of the material itself, as well as also very, very long, again, reliability and robustness. I'll show you one piece of actual data that we've done from a lot of extensive testing that we've done internal to TI on this capacitive technology. What I'm showing you here is essentially data from actual tests that we've done at Texas Instruments. This is done on almost 2,000 different devices from multiple lots picked from our assembly lines at multiple times. If you look at what this shows you, the y-axis over here is just number of devices. And the x-axis over here is the test voltage to barrier fail. Now TI, we have one of the highest overvoltage specifications for a digital isolator in the market today. That, the datasheet spec will tell you it's 5.7 kV RMS. We actually tested these devices to failure to try and see how much margin we have. If you look at the spec, it's 5.7 over here. But fundamentally, the devices begin to break down far in excess of that number, more than 2x higher. Now, this kind of margin is very, very important for us to be able to make those reliability and robustness claims. Since this is a safety system, it is critical that the device is extremely strong, and this data basically proves it. The other key point I'll make on this slide, which is very important, is if you look at the tightness of this distribution. Now, remember that I said that this was 2,000 units, and these are again units picked on different devices at different times from our assembly line. You will see that the data is extremely tight and extremely well controlled. This is what I mentioned about from a reliability and robustness perspective. It is not only important to be able to meet the spec, it is also very important how well controlled our manufacturing processes are. And this is a key data point that proves that. What this shows over here, if you look at this data, is that even though the average breakdown value is 12.35 kilovolts RMS, the variability, that is how much one device with respect to another device over a long period of time varies, is less than 260 volts. 0.26. So this kind of manufacturing tightness is critical to have a high quality safety device like the isolators that TI has. The other point I'll make is, what have we done with this very exciting technology that we've been able to create over the past few years? TI has a very comprehensive isolation portfolio. We've got digital isolators and digital isolators plus power. Basically, the digital isolators are, we've got multiple channel counts, and we've been able to get some of the smallest form factors in the world by putting up to 6 channels in very, very small packages. What we've also been able to do is integrate an isolated power supply, an isolated DC-DC power supply within the same small form factor that we've got. And this is something that provides a very high level of not only reliability, but also flexibility to the system designer. We've got isolated interfaces. Basically, we've taken the best transceivers that TI has to offer and integrated them with a digitally isolated barrier also. So from an isolated CAN, RS-485, I2C, and LVDS perspective, we've got comprehensive solutions for pretty much any communications need. Gate drivers, TI also has a comprehensive portfolio of gate drivers, not only for IGBTs, but for MOSFETs, as well as we're also getting able to use some of this technology for silicon carbide and GaN as future technology, simply because of the robustness that is available on this technology. ADCs and amplifiers, for the other side of, say, a motor drive system where you have to sense high voltages, high currents from the hot side of a system and bring that information back to the cold side. We've also got highly integrated ADCs as well as delta sigma devices with the isolation barrier integrated. So with that, I'm going to walk into a couple of the products that I'd like to share with you today. The first one is essentially an isolated amplifier. The part number is ISO1042, and it is meant for voltage sensing. So the 3 things that I'll talk about, among the many other advantages that a part like this actually have, are it has the highest reliability, which is essentially half as much or 50% higher working voltage for the longest lifetime and reliability. Again, you'll see that this is a theme that we keep talking about throughout this particular process, because some of the most important things for an isolated system are exactly that. It is reliability, robustness, and lifetime over very varied temperature conditions. Industry's highest performance, basically we have in this particular device the highest accuracy measurements of plus to minus 12 volt systems, and I'll walk into that a little bit more in detail in a little bit. And also a device such as this actually provides much simplified design and system diagnostics. It has an integrated voltage detection feature also that we'll walk into a little bit on the next slides. I touched briefly in a previous slide about, we talked about the longest lifetime that we actually had. Now I'd like to walk you in a little bit more detail on how is it that we make these lifetime claims. In the data sheet you will find that we say our barrier lifetime is modeled up to 40 years. And then the actual modeling value that I'm going to show you over here has even higher numbers than that. To tell you how we do this testing, we use an industry standard methodology called TDDB, which stands for time-dependent dielectric breakdown. And this is the same kind of test methodology that is used for any insulative material, whether you're talking about glass, PVC, rubber, plastic, whatever it is. This is industry standard. It's been used for many decades to actually test what an isolation system is capable of. This is how we model a system for very long periods of time. If you look at this curve here, the y-axis is time to fail in the number of seconds. And the x-axis is the test voltage that is applied. The y-axis is in an exponential scale. So whereas this is 1 second here, over here is actually 40 years. So it's an exponential order of magnitude kind of system. The way we do this testing is, first we pick a very high voltage, assume that that is about 7,000 volts. We test many parts, 100 parts, 200 parts, at 7,000 volts. We stress those devices and wait till a statistically significant amount of them has failed. Once the failure has been reached, we find out what time that is, and we plot it on this curve. Then we do the same test for 6,000 volts, and then we plot the failure time. 5,000 volts, we plot the failure time. So now if you look at it, you're able to actually get a very precise model from a time versus voltage perspective of what the failure looks like with respect to lifetime. So if you extend this curve all the way up, you will then find out what voltage, at what voltage level you will be able to get 10 years, 20 years, 40 years, whatever it is. So this is the methodology by which we decide what our isolators are capable of from a lifetime perspective. So here are some of the key specifications that we're talking about for the latest ISO1042 amplifiers. We've got 2 grades of performance that we've actually released for different places in the market where we can go off and attack this. And you'll actually see that, again, the theme is in harsh environments you have the highest performance. So basically the highest accuracy measurements of up to plus minus 12 volts signals with very low offset and gain error. These specifications, if you look at the competitive landscape of isolation amplifiers, we pretty much have some of the best amplifiers out there. And it's based on the fact that we've got not only an excellent isolation technology, but also the ADCs and the DAC elements that we have to use to implement an isolated amplifier are some of the best from a performance standpoint that we've got. We also have a much faster system response, given that most systems these days, though they begin at lower speeds, you do have a move that we are seeing to higher and higher bandwidth needs. So these are some of the use cases where we actually use this particular amplifier. You'll see that the top schematic over here is the primary use case, where we have essentially an exciting signal in the left-hand side where the amplifier senses that, sends the information over a digital isolation barrier, recreates the signal on the other side, and you have some of the a very high quality rendition of what that signal looks like at the output. The input, as we mentioned, can go from plus to minus 12 volts. And the output can be connected directly to an ADC with a 5-volt input. Also, almost as important these days, diagnostics in terms of whether the amplifier is working correctly or whether the input signals, what the status of the input signals are. These are critical items. You'll actually see that in this particular case, if you have a 0-volt input, you will see that both the outputs collapse to a common mode value that looks like that. So the system that is looking at it on the other side is able to tell that the input has gone to 0. On the other hand, let's assume for a moment that you've lost power supply on one side of the isolated amplifier for whatever reason. It could be a fault condition. Then you now have a different condition where the output is still differentially 0, but the outputs collapse to ground. So features like this are becoming very important, along with a very high performance output. Also, some of the diagnostic features are what makes the ISO1042 a really good device. So I'll try to move along a little bit faster to give you guys some more time. We also have a couple of videos, I think, at the end, and also leave some time for Q&A. But the other point I also wanted to talk about was the ISO1042. We're very proud of this device also. It is an isolated CAN device that has very future-forward features. So we're talking about the smallest reinforced isolated CAN that is capable of flexible data rate speeds. So basically higher speeds, 2 to 5 megabits per second are possible. And it is married to some of the best isolation technology that TI actually has. So what we've got are highest working voltage. We've already talked about that. CAN FD. This is one of the latest CAN standards, the flexible data rate capability that allows a CAN network to run at 2 megabits per second or 5 megabits per second, which is more and more necessary for more and more bandwidth constrained systems. It has the lowest emissions. This is again key. A CAN system is something that runs long cables, whether it's in a car or in an industrial system. It cannot make much noise. And what we've got with this device is the lowest emissions as well as the highest immunity. And I'll talk a little bit more about that in the next slides. And also, it has the highest bus fault protection. Again, we're seeing a move to higher and higher voltage systems, whether it's an industrial or automotive. We're going from 12 volt to 24 to 48. This particular CAN device has a very high bus fault tolerance that is going to be very good for the higher voltage systems. So again, we talked already about the way we measure the insulation lifetime to provide the highest working voltage. I will not spend too much time on this. I'm going to go to the next slide directly. So this is what I discussed briefly at the beginning about the CAN FD. As you know, even industrial networks, though, if you look at the last mile from a sensor perspective or anything that has low speed information, the data rates are not very high. But if you start thinking about the fact that in a car today you could have anywhere from 30 CAN devices to 100 devices, and it's the same situation on industrial networks as well, you begin to start seeing the need for much higher levels of data throughput. So where we are seeing the world move is away from the 500 kilobits per second or 1 megabit per second that CAN networks typically work at, more to doing 2 megabits per second on complex networks as well as 5 megabits per second in some cases. This particular device brings a lot of advantages to be able to run at higher speeds. A particular item from a specification that I'd like to talk about is the short loop delay. Loop delay essentially means the entire amount of time it takes for a bit to get transmitted, go onto the bus, received, and come back. So that entire loop in this particular device is the shortest in the world today at 215 nanoseconds. The bottom line is, with the lowest emissions and the highest immunity, as well as the smallest package and the highest isolation ratings, this is one of the devices that you can build an entire system around for the future. The other thing I talked about, and I'd like to touch upon again, is on a CAN network, some of the most critical aspects of it, once you get the functional characteristics out of the way, are emissions. That is basically how much noise it makes and emits into the world, as well as immunity, how robust it is to external noises and influences like ESD, EFD, and whatever else have you. I'm actually quite proud to say that this particular CAN device, the ISO1042, has the lowest possible emissions. You'll see that in this curve, this is essentially an automotive emission limit curve that I'm showing you here. It is a test that is done by the University of Zwickau. And you'll see some of the numbers over here. It's a TS62228. And you can see that we pass this particular curve. This is a very difficult thing to do. But even with a digital isolator and a CAN integrated in the same package, we're easily able to meet these emission specs. Immunity also, we have very high levels of immunity, not only from a CAN bus standpoint, but also from a high voltage standpoint. I didn't specifically talk about this till now, but all our isolation devices have world-class CMTI performance, that is common mode transient immunity. What I mean by that is it's a measure of how much noise the digital isolation barrier itself can tolerate without losing a bit. In this particular case, we're talking about 85 kilovolts per microseconds minimum. What I mean by that is typically, even if you have 100 or 110 kilovolts per microseconds, that is that much noise across the barrier, these devices will not miss a single bit. Our spec is a very conservative spec because Texas Instruments believes in being very conservative in the data sheet. 85 is the absolute minimum. To give you some perspective, most systems, even a very high-speed switching GAN system, for example, will not even hit about 50 to 60. So in terms of being extremely immune in all senses of the word, as well as being extremely quiet, we have a device here that is pretty much the best in the world right now. So I also touched upon the higher voltage nodes that basically more and more systems are being designed at, and want to talk about the bus fault protection capability of these devices. The ISO1042 is capable of up to 70 volts of standoff on the bus. What that means is, in a 48-volt system, if you short circuit the bus by some mistake, some fault condition, the device itself will not die. And this is critical for newer systems, both industrial and automotive, that run at 48 volts, for example. It is very suitable for everything from 12, 24, 48, and very extensible into the future as a result. Yeah, at this point, I'd like to actually, let me just make sure. So a couple things I want to talk about are we've actually got an ISO1042, that is the latest device demo, and this is going to be on display at Electronica, Messe München, and also at CES. So if any of you are going to be stopping by our booth, we invite you to please stop by and take a look at it. We do have a picture here. We've got 3 different ways of doing an isolated CAN network. You can see the 3 different ways, and all of them have both isolated power and different varying stages of integration also. The key thing I'll point out, in this particular demo, we've got 30 meters of cable within those 3 CAN nodes, and all of it is easily able to run at 5 megabits per second. So this is very critical because now we can do higher speeds at non-ideal networks also. Yeah, and at this point, I'd like to also, we're probably going to share this information also with you, but there's lots and lots of tools as well as support for both the ISO1042 and the 1042 online. We're also working on putting a lot of this material as well as a lot of different ways in which to get the best of these devices, and all of it is available to you on TI.com. At this point, I'm going to invite my colleagues here to show you a short video before we head into the question and answer session. And I also encourage you to go to the tools and support page, which has a lot of the high voltage materials. But yeah.
Hello. Today I'm going to show you a showcase in the interoperability of various isolated CAN systems. 3 different configurations of isolated CAN and isolated power. Virtually employs a discrete TCAN1042 with a discrete isolator, ISO1042 for the data communication. A transformer driver, SN6501 with external transformer and regulator, constitute the isolated power section. The second configuration uses a similar discrete isolated power section with a higher output current transformer driver, SN6505, but for the data path, the isolated CAN transceiver, ISO1042, is used to save space. An integrated isolated data and power chip, ISOW7841, is used in conjunction with the discrete CAN transceiver TCAN1042 to create an even smaller third solution. In this demo, we are showing 2 boards communicating with each other on a 30-meter CAN-FD bus for each of these 3 solutions. The GUI developed for this demo shows the number of packets sent and received by each board, as well as any errors. As you can see, no errors have accumulated on any of these devices. We also have a speed gauge, which shows the data speed in which each device is transmitting and receiving, as well as some analytics showing the bus loading. While operating at 1 megabit per second, the bus is about 40% loaded. At 5 megabit per second, the bus loading reduces to 15%, and the transceivers can still communicate reliably. This shows faster CAN-FD speeds not only allow faster communication, but it can also allow for more devices on a single bus. In addition to CAN-FD speeds, all 3 solutions shown here also have high isolation ratings, making them suitable for basic and reinforced applications. For more information on these solutions, visit ti.com/isocan. Thanks for watching.